Don't tell me it's the Friday time again, is
Oh,
it?
it's Friday. That means
Yes.
we're live, right? I thought it was just like any other day, and it would
Yeah,
just be
staring at each
sort of,
other in the monitor. Yeah, of course.
yeah.
No, no, we're actually live.
Okay.
So,
So what's going on?
what's going on that we were busy understanding what was going on from a performance standpoint. And so we want to see, like just wrapping up what came before, we are trying to adopt the Liger kernels or take the Liger kernels. Liger is a project by LinkedIn to make training faster on LLMs. They're optimized Triton kernels, OpenAI Triton kernels. And they have been kind of created to perfectly fit Hugging Face transformers, and we want to apply them to a code base that are completely unrelated. And we want to go through the whole exercise of making that compatible, then finding out if performance is good, if it's not good, digging more and learning something from the process. Now, we're at the point where they are integrated. The performance is still not what we would like, and so we left it off. And to be clear, we're doing this work kind of real time. So we left off trying to understand where performance was, and so now maybe we can also dive into like how do I get a better understanding or where we spend time at the various parts of the stack, and then how do we bisect the problem and see what is fast, what is slow, what works well, what not. So that's a learning experience for all of us, except, well, including Thomas.
Yeah, I probably learned the most.
All
Uh,
right, let's get to it. No drawings today, just code, code, code.
okay, let's see where we're at. We have the Thunder bindings for the Liger operators. And of course, if you want to play along at home, the notebook is also uh, uh, in the Thunder repository now. So if you look at Lightning Thunder, uh, yeah, I always have the issues on by default, but let's not talk
Of
about
course.
issues so much. But so here's the documentation, and in the documentation, we have Thunder bindings for Liger, and you can play along. And it started episode 10. I think we're at 12 now or so.
12.
So we will see how we take this further, right? And I've opened it up here too. And so where we were last time was that we had implemented RMS norm and also rope uh, and Swiglu, and finally the fuse, cross entropy, and linear. And so these four we added to an example model here, and we had to adapt the standard LitGPT model a tiny little bit to have this fine tuning setup that the example from the Liga repo used. And we will chat a bit about like the hand optimization we did here. But so long story short, we ran this, and then one thing we noticed is that probably we want to look at performance a bit because because we do we run this? Yeah. So we want to look at performance a bit individually. So there is one thing that you should look into: how is the data loader doing, and is that fast enough? And the answer might be probably not yet. But so for Thunder, we're focusing on the GPU model, and so we have three of them here. One is we compile basically without the Liger bits. So the I executor here is a bit of a cheat because we need to provide a mask to the attention that like uses an I-shaped matrix under the hood, and because I think I is not yet supported in Thunder, so I made a little executor just for that. But other than that, we're just running with the default executors, and we can time it. It's like silly timing here that we're doing. We just call time it, and then we call the model. Oh, but here we want to time the model with the original kernel. So I'm going to copy this to a new cell, and so this is plain plain Thunder, and so we had this timing, and then we had the timing model.model. That is the one we compiled up here. And what did we do here to it? So we had thunder.jit here with the Liger executor, the special I executor, and the default ones. And we had our 3 fusion operations. So we have those, and we can run it with them. And then we finally have the eager one, where we just run the model in plain PyTorch. And so we see that the Liger one is a bit slower, and not like a little bit. But so here's the first thing we did. We didn't actually measure what is important in terms of timing here.
Yeah. So not everything is isotropically slower. So when you see these numbers, you shouldn't go on LinkedIn or Twitter and say, "Oh my God, Liger, it doesn't work." Blah blah blah. There's always one thing that is probably the bottleneck, and so that's what this investigation is about. And it's nice because it's a very real world situation. It will happen all the time, and if it doesn't happen, probably you're not noticing it.
And also optimizations are necessarily always for a very specific scenario, and we will see that we deviated from that scenario. And so one of the things we're doing totally different is that in a fine-tuning scenario, you typically backpropagate the loss, right? So I'm going to mimic this here by saying output some backward. And then we also need to do this here. And the reason this is important is because that's our actual workload we're interested in profiling. And it's easy to forget, but then Liger has some things in particular for the fused cross entropy, where it actually performs the backward during while being asked for the forward, because they're specialized for fine tuning, and so they expect to be asked to compute that next, and they prepare for it. So we're now at 90 milliseconds with the plain Thunder, and we're at 99, so it's not like 30% slower, but it's just 10% here. And with the eager, I think we're coming out close to the Thunder one. Not quite there, but close. So we have these 3 data points if we want. And now is we can ask ourselves, like, how do we decompose this in order to figure out, like, what is being slow, right?
Yep, exactly. So some of it is get a better tool out of like the thing. So time it is very like high level. Although if you break things up and still time the parts of the model, you can still get a lot of information there.
Yeah, and maybe that's one thing. Last week we also started looking at the PyTorch profiler, which is an awesome tool to understand what's going on. But we can also take it a bit further here, because one of the things we did here was to compare the plain Thunder, and we can actually do it a bit more nuanced by
Mm-hmm.
adding in the Liger executor here. So what will this do? It will take the things that where we actually implemented a replacement directly, but it will not apply the fusion transformation. So effectively, what we're doing is we're taking just the RMS norm implementation from Liger, and we can compare this to the 90.8.
Yeah, let me explain for a second what's happening right now, just to so that if
Right.
you already have a mental map of how Thunder works, that's this will sound repetitive, but it may make you click on Thunder a bit more. So Liger executor has all the Liger executor, Liger X in there, has all the kernels that Liger comes with and the driving function for them, right? So whatever you need to actually launch them. And then, of course, the executor, once there's a trace to execute, uh, will say, okay, I can take this operation and then run it through a certain kernel, right? Now, if you don't fuse and replace, like Sweetloop, for example, is composed of two operations, and we fuse them into one. We removed, using the transform, we removed the two operations and we replaced them with just one of them. And that one of them maps to the executor so that the executor can take them up. But if you don't do that, if you don't replace the two operations with one, the executor will not find anything to execute there. And so we did a few fusions, three of them, and then we had a fourth that was RMS norm that was already in the form that Liger had kernels for. And so when you just use the executor, it will just pick it up. And that's why by not specifying any transforms, but just specifying the executor, the only operation that executor will find in the trace is that RMS norm operation.
Yeah, and that is not 100% true. The trouble is that we defined the symbol apply rope in order to find it easier. And if you look just now, you saw that Thunder complains about the VJP of this apply rope not being defined.
Oh
And
yeah, because now we do backward.
that is expected. But so one of the
so
solutions.
you removed backward.
Well, so I removed the apply. It will also happen if you just require gradients, because you also need the forward that saves required parameters. But so what I did is I skipped this registration of the apply rope operator.
Oh, okay.
And now it just applies the rope as is. So one way we could avoid this is by specifying a backward. That would be the easiest. The other way to do it can be to define an autograd function, because then Thunder will automatically pick up the backward that is from there. But so now we need to rerun the notebook minus the one thing, and then we hopefully get the comparison point where we only have the RMS norm, and then we can enable the rope next, right?
Yep. Yeah. Yeah, the autograph function thing is actually the compatibility between autograph functions and understanding them is pretty handy. You can find autograph functions around in the wild, and you don't have to rework them or understand how to write specific Thunder things, and you can just use those.
Yeah, you used to have to like define a lookaside and something particular for the autograph function, but nowadays it's a relatively recent feature from Masaki, one of the NVIDIA colleagues, implemented this, and now it will just go into the autograph function and it will find the forward and the backward and automatically register them for you, which is pretty nifty. But
Yep.
okay, so we're now
Nice.
our model, and let's hope that it will work. I'm relatively optimistic, but you never know when you do it live, right?
Yeah.
All work during rehearsal, maybe. Okay,
So, yep.
it worked, and now
Okay, I was going to say something, but now I'll wait. Yeah, I'm too curious to see what's going on here. So let's see. It was 90 before, right?
So it was 90 before. So actually, the rope gives us the RMS norm is a bit faster than it is without the RMS norm, and so we can.
So just playing it back again. Sorry, I'm being redundant here, but what we did is we took all the Thunder optimizations that Thunder does by default without knowing what the model is, whatever. That gets us a bit faster than Eager. But then among all those things, we said, okay, instead of using just MBFuser and whatever is used in the default executor, let's also use RMS norm from Liker. And we get 3 milliseconds. It's not bad as a speed up. So we're now 5 milliseconds faster than Eager.
Yeah, so I mean,
interesting.
It's 4% or something like this, right?
Yeah.
You have 3 milliseconds, so it's for end to end. It's not like
not bad.
A small thing, right? And so we can look at the bound symbols here. And what I like to do is I like to get me the names of them. So BSIM name for
this is where Thunder is super handy, and maybe will become even handier in the future as we work through this. But the level of introspection here is interesting.
Okay, so what we see is we have lots of sections that are torch compiled. We have lots of NV Fusion sections, and then we have here the Liger RMS norm forward. So this is actually happening. And we don't see any other Liger ops, which means that we have just the forward, and we got the speed up from that. So next would be to also enable the RMS norm, and also the rope.
We did, the rope.
I didn't so far, and I'm scrolling too much, so I'm sorry. And so in order to get that into here, we need to add the transform parameter. So transforms, and the transform we need is the merge rope transform. And of course, in order to make this work, I need to scroll up, and I skipped one of the cells here that did the rope registration. I'm just going to add it now. And we can see what we get now. Thunder needs to recompile this.
We have some time to chat.
Yeah. So we're
Which
at
leads me to an interesting thing. Like you saw that PyTorch 2.5 happened yesterday. That's great. That's awesome. Go
right.
read the blog post for whoever hasn't. One of the things that the Torch Compile team added is whenever you have repeated blocks in a model, they just do the compilation once. I found it very smart and interesting to reduce the compilation time. And so we're using Torch Compile as an executor in the back, but while acquiring the program, we don't take advantage of this feature. But we could think about something like that for Thunder as well.
Yeah. So with
rope, 1 millisecond.
We're squeezing out another millisecond. Let's see what
that's interesting.
We have here. We have the Liger rope forward. So
yep.
That's in there too. So the custom rope gives us a small speed up as well. And so we're doing pretty good here, I'd say.
Yeah. Not bad.
Obviously, congrats to the Liger team because they made all this great kernels.
We're sitting pretty here.
And okay, so the next thing we can add is the Swigglue. And I just need to add the transformation here. And obviously, one of the things we could do is not like rerun the Python interpreter that is running in the background right now.
Of course.
But then what would we do for chatting?
Yeah, because we've already acquired our trace, so we could just say, okay, this is your trace, initial trace. Now add a transform. It would be really awesome, I think, to work on some of these developer UX things in the next few weeks and months, and I think all these things are up for grabs, and we have all the pieces to make those happen. It's really interesting. All right, we're there.
Oh,
didn't make a
tiny bit slower, right?
Yes. What's going on? Swigglue, you probably NVFuser does a better job. That's what it is, maybe for the sizes that we have. So, dear Swigglue kernel, we love you, but not enough.
And so, so we can also like get this here again, and we see here's the Swigglue, and we're going to take you out. And the other thing we have is the cross entropy, and but if you have like ideas about it, you probably have a guess whether it'll get faster or not faster. And so one of the things about this here is that the fused linear cross entropy transform, I think it also saves like a bunch of memory because it will compute the gradient directly into the space where you have the activation, which is very nifty.
Although, LibGPT has... sorry, go ahead.
No, you go.
LibGPT has chunked cross entropy, which also aims at reducing... 98! So we found what was not great. Yeah, so I was saying that LibGPT has chunked cross entropy where you chunk the computation of cross entropy so you don't have a huge memory spike when you go through cross entropy, because that's a real problem, right? You may be okay storing the weights, the activations, the optimizer state, whatever, throughout the computation, and then comes cross entropy, and you have a huge spike there. Your GPU goes out of memory, you're out of loss. You need to either run on multiple GPUs or reduce your batch size, but maybe it's already one. it's a disaster. So now this aims to solve that problem as well as be fast enough, but we just
Right.
found out that it's not fast at all.
Yeah. So now we need to decide a bit what we're going to do. And so one of the things we can do is we can look, well, we always should keep in mind like what kind of model we had. So let's look at it. It's the Llama 1 billion model, right? The
Yep.
new one. And so remember that we ran the LM head, and then we had the cross entropy loss applied to that, and we fused it. And so in order to make profiling a bit easier, we can make the assumption that all of the hidden layers, the 16 blocks, don't actually contribute to the performance difference that we see.
Yep.
And so we can skip those. And I will do this in a very, very
brutal way.
Brutal way if you want. So I'll just go and say model, and it is transformer. Is it no, I need another layer. So model. So we unwrap the Lightning model, which contains a model which is our LitGPT Thunder model, and that has a model which is the original one. And so you see that people that have the same problem, that they need to wrap something, they always have the same idea about naming. But at least we can access the original model that way.
Yep.
And so these are the hidden layers, and we will just clear them. So does clear work on a module list? No. So
interesting. Open an issue on PyTorch.
Well,
maybe not. Maybe it's intended not to happen.
Yeah, I mean, it's kind of a very special interest used here, right?
For sure.
Okay, so this should like make the compilation considerably faster. And this is something like if you're working on anything, do care about your turnaround time, because otherwise it will be really, really bad. And so we will compare it with model. Well, no.
So right now we basically have an embedding, the head, and the loss. That's it. That's all our model, right?
Right. And so we can now take out the fused linear cross entropy, and we can benchmark it.
Let's see. Very curious.
Oh, and now this difference is very apparent.
Wow.
Also, like the trace got a lot simpler because we're not doing much anymore, right?
Yeah, see the power of surgery, right? Now we can stare at all the ops in one little cell. So we're embedding. Oh.
Yeah. You.
Okay. Yeah.
So we have embedding here, and it's decomposed into sub-ops, and then we have the RMS norm, the fused cross entropy layer, which will be like unfused in the other model, wherever it has all these sub-operations. And I wonder if that is part of our problem.
Which one? Sorry, can you say it again?
So it has all these sub-operations still on there, and I wonder what's going on with that.
Hmm.
And
Yeah, I
so
see.
let's go
Because
back.
it could be like you should just have the op and that's it, right?
Yeah, let's go back to the transform. And
Maybe the backward is not defined. I don't know.
well, so the subsymbols should be nothing for the forward.
Yeah,
So it's
interesting.
very, very curious what's going on here. So Liger, fuse, cross entropy, linear, forward. Let's get that. So this will be, no, it will not be it will be this one. And this clearly has subsymbols. Yeah, why does it have these? When in the transform, we clearly ask to clear it, right? Where is the transform? And so this is the thing where the live, again, kind of has it. So I would say we're trying to clear it here. And I wonder what's going on. So do you see what's going on? No. So let's
No, I don't, because we have the symbol, the name symbol there. So we're using the Liger one. What is the name
yeah.
of the symbol? Is that the right one? Yeah, you
Well,
need to show the. Yeah.
so what I was going to do is have the transform printed, and so
Yeah.
now,
Before and after, right?
well,
Maybe.
so now it just calls the Liger fuse cross entropy forward, and so now it has the bound symbols again. But let's look at where they actually start. So if we go back, like the series of transformations, let's start with the initial trace.
Exactly.
There will
So
just
right now, what we're doing is like we're going from the acquired trace on as transformations get applied, and we see how the trace changes. And we can
right.
do that by just changing the index there.
Yeah, and we have the linear and the cross entropy here,
Yeah.
and in the next, let's not specialize on the bound symbols. The next is by return arguments to track copies onto them. There will be some internal thing. So now it is the merge rope transform, and that is still not the one we want, right? And now it's fuse cross linear entropy. And so let's see what's going on here. And here we have the thing actually without the,
Haha.
without any implication. And then
Yeah.
something adds it back. So
Yes. Not yet.
not
Nope.
the
It's
dead
not.
code elimination.
No, that would be weird.
Be even more weird, right? And so
Yeah.
here we still have the thing without anything. And now the augmented forward
Maybe
pass is the
that's a
thing
backward.
that does
Yeah. I
weird.
called it before. I called it.
Okay, so apparently, and I know what's going on now. So what we did was we tried to be clever here, and we registered the operation with a like function that just did the linear and cross entropy, and so that is a bit bad apparently. And so what we should do instead, we know that in our case at least the cross entropy loss will be of scalar shape, right? So it will be just like a tensor proxy like the input, but with a shape that is empty, which means it's a scalar.
Scalar, yeah.
And so now I changed that to meta because you can have a meta that has a decomposed thing. And so now we can run this again, and it's very quick. And if we time it, it will be interesting. But it's still slow. So one thing.
Well, let's look at the trace though. Did we already? The final one, the -1.
You think that it's still doing its thing?
I don't know.
I think
we don't know.
Right. Yeah, we didn't.
Okay.
So what did I do? Did I?
Yeah, I think it has to do with the meta, for sure. Either for the backward or the forward or wherever, right?
Yeah. So.
But did you recompile? Maybe. Oh yeah, you did, right?
I thought I did, but let me look at this more. Maybe we'll just like restart the notebook and rerun it to be sure that everything is like in pristine state. Which is one of these things, right? If things go too confusing, then
just close your computer. No, reboot
There's one of my favorite jokes. So I'm not a computer scientist by training. I'm a mathematician. And so one of my favorite jokes is there's 3 people, chemistry, a professional or someone who studied chemistry, someone who studied physics, and the computer scientist. And they're in the desert, and suddenly their car stops working. And so the chemistry expert, he'll say, oh, it's the carburetor. When it's so hot, we need to adjust the mixture and stuff. And the physicist says, well, no, it's the transmission with the sand, and we need to clear all that. And the computer scientist says, well, let's open the doors and shut them again, and maybe it'll work.
Yes.
And so
yeah, very true, very true. And actually, I'm not a computer scientist either, or by trade, but not by training.
Right.
But I've been doing this for a long time, and then I did some hardware stuff. I remember my postdoc some experiments, and not being able to reboot your botched timing NMR scanner. Well, like not great. So yeah, it strikes you immediately.
Yeah.
It's not just a joke, it's actually true.
I mean, this is something like programming medical devices. I think that is a whole different, I mean, it's a other league of responsibility they are accepting.
Yeah, you have the brittleness of computer science and the risk profile of
medicine,
of an airplane.
Right.
Yeah.
Okay. So
Let's see. Let's see. Let's see that it's making progress.
so one thing we could also do is like add a print to whenever our kernel is called.
Mm-hmm.
Uh, so I will do this in the. Oh, I just call the function directly. So it's so I'm going to be a bit lazy and just do this with args and quarks. And so I will print the fused linear cross entropy called, and then I'll call the forward function. And now you see that, like, yeah, I should be better than that, but that's how I personally like to do debugging. Just insert a few prints.
Yep.
And you have args and quarks, and then we'll see what happens. Okay, so this ran now, and do we have like, oh, and now we don't have any
Yeah.
like other
Nice.
things anymore, and
And what's the timing? I didn't see
continues
that.
to be -1, and now Luca wants to see if we secretly ran all the wrong things, but the timing didn't change, so we actually ran the right thing. And this is when Thunder has an executor for a combined symbol, a higher level symbol, it will take that over the decomposition.
Yep.
That's only relevant when you have fusing executors like NVFuser or the Torch compiler one to have this. Okay, but
Exactly.
so
Because
now
the
we have
breaking down. Yeah. Go ahead.
the difference here, and one of the things that might be happening is we changed a little bit how we actually do this, how we call the operator, and that is that we specialize. We notice that in the data set, it's always only the last uh, uh, or the second to last prediction that gets chosen for the loss, and all the others were masked away. And so we did
Yep.
this. What we did is we just grabbed the bit that we wanted and only called the last linear layer and this on that. But this means that, oh, at least the inputs here are non-contiguous. But if we have the normalization, the output would be contiguous, right? So we will have to see, like, why is this operation slower? But we narrowed it down to something that's very manageable, just a few operations. And now we can run this through the PyTorch profiler. And
Mm-hmm.
let's do this. So it's model default exec, which is with everything. And then we have the model no fused linear cross entropy. And so we can now here, yeah, I need to set up my screen
Zoom
better.
out. Yeah. Yeah. Okay.
But so we can now check, like, what is the total self CUDA time, um, and see what's slow. And but looking at the time, I think we should do this next week. So
Yep. Yep. Yep.
let's
All right.
summarize what we did here. So we had these
Yep.
4 Liger kernels, which in our specific setup didn't give us the speed up that we wanted. The first thing we noticed is that we actually measured a slightly wrong thing, only the forward last time, so we fixed that. Then we enabled our proposed optimizations one by one, and we found that 2 of them, the RMS norm and the merge rope, gave us good speedups. And so that's great. We have speedups there. And then we also saw that the fused linear cross entropy, that didn't give us the speedup that we wanted. And in fact, it caused a slowdown. Again, in our specific setting. And this will be something that we will look at. Like, we will want to know which kernels are being called, when are they being called, and how long are they taking. And we will use the key averages here, but we will also look at the timeline for this. But that's next week.
That's for next week. Okay, nice. We understood a lot, like from an aggregate number. Now we have the breakdown. We followed a red herring at some point with the, we saw that Thunder was breaking the fused cross entropy down in primitives, which is not a bad thing per se, but we were worried that what we would pick later on would be the breaking down into primitives. So although Torch Compile or MDiffuser could fuse them happily, but that would mean that we wouldn't have been, we weren't using the Liger kernel for that. And so we made sure there was no primitive breakdown, but the timing didn't change, meaning the executor was picking up the right kernel. There were other ways to check that, but we checked it that way. Now everything is clean, ready for surgery. So next week we'll do surgery and measurement with the profiler. Thanks a lot, Thomas. It was a great journey, great way
Thanks,
to
Luca.
end the week.
And
thank you so much, Thomas.
And a good week
You too.
See you in a week.
See you. Bye-bye. Thank you.